episode here on in the TSA lab, I should say. And welcome to the podcast. And the first couple of podcasts we've done were on static pressure, and we preach static pressure tremendously here because this is something that ICP is passed down to push down about longevity of your units. Now, we're going to talk a little bit this week, or this episode, about why compressors fail and the working mechanisms of a compressor and the terminologies that are used for a compressor, and to understand what's inside the compressor and what each component does, and then how to keep your compressor from self-destructing. So we're going to talk basically, this is for residential scroll compressors, the basics of it. And if you took one and took the top off of it, right there where the weld is, let's say you just cut that and you pull it off, you're going to find the scrolls, the two scroll plates right there. And the scroll compressor is a moving scroll that orbits about a path defined by the fixed scroll. So you have the fixed scroll on the bottom and you have the moving scroll on top. They capture the pocket of gas that comes in through the suction tube. Now, when you look at these compressors, and we tore apart the LG and we tore apart the Copeland, when you look at those compressors, they are hollow, okay? So I want you to understand what I'm about to tell you, because I'm going to try to paint you a picture of what you're going to look at. All the components are in. So you have the oil that comes in. Let's say your oil that's in the bottom of the compressor. And then you have a ring that kind of holds that oil in place in that area. And you have a seal. Then you have the shaft on the motor, or the rotor part with a motor on it. And then you have your windings around that, and then you have a bearing that sets on called the overload bearing, and then you have the oddman bearing and different ones. But on the suction, when your refrigerant comes in, it fills up that compressor cavity. That is what cools the compressor. So I want you to think about a blower motor in a unit. A blower motor, when you look at a blower motor, the end of it has holes all in it. So the air that is pulling through the house actually cools the windings in the motor. That's how it keeps it from overheating. So you understand the concept. When a motor slows down, the windings get hot and a motor goes bad, just like a compressor will. So if you don't have enough freon, enough charge, or you have it blocked, or it's not, the suction line's keying to water, it cannot cool itself, so it's going to go off on internal overload. So if you have a low charge, the compressor cannot cool itself properly, so it's going to pop off on what we call the high side, or high limit, or high head pressure will pop that internal off. So you got to look at that. So this thing fills up with gas, and as it comes in, it pushes the refrigerant inside the scrolls, and the scrolls are like orbiting and pinching at the same time. If you ever look at the diagram, some of the gas comes in and it pushes it into a tighter pressure, which forces it up through the scroll, and as it orbits, it keeps pushing and making it higher pressure, and then it finally pushes it out the top, and that comes out of your discharge line at the top. All right, so it's a fixed scroll. It has a capture and a pocket of gas between the two screws, and then forces it into an increasingly smaller packet, resulting in the compression. So if you look at the screw, it's got these long cylinder shape. As it comes in smaller, both of them come in smaller, so it makes the channel from going pretty wide being compressed down to a very small area, which forces that into a high pressure gas. So the refrigerant enters through the suction tube. The moving scroll orbits about the fixed scroll, which is driven by the crankshaft, and you have the oddman bearing that sits under that fixed scroll that lets that move back and forth. The refrigerant is forced to follow the path created by the moving scroll inward toward the center of the fixed scroll. As it approaches the center, the pocket grows smaller, and the temperature and pressure of the refrigerant increases as a result of that. The compressed high-temperature refrigerant is then discharged from the center of the scroll and out the discharge tube. So if you look at the very top of the compressor, that's called the top cap and a muffler plate. If you was to cut that off, you see the top plate, which is domed, and then underneath that, you'll actually see a muffler plate. Well, in between the muffler plate and that, you have the discharge tube. So the Freon goes up through that muffler plate and then comes out through the discharge fitting or the discharge tube. So the top cap creates a sealed cavity for the high-pressure vapor. Discharge fitting and check valve connects top cap cavity, I'll get it out in a minute, into discharge line and prevents backflow into the low side of the compressor during shutdown. Now the muffler plate, if you flip that over, and you'll see the muffler plate has an IPR and a TOD. So we're going to talk about those two for just a second. The muffler plate provides the separation from the high side to the low side of the compressor. So you have your suction coming in, and as it goes through the scroll, that muffler plate divides the low pressure from the high pressure. The TOD, or the thermodisc protected device, routes excessively hot discharge gas towards the motor protection system, which then temporarily stops compression operation until the motor has cooled. Again, you have the windings and you have the motor and all this pressure getting up where it's not getting cool enough, or there's too much pressure going in and not enough coolant to keep the motor cooled. It will trigger that thermodisc to shut the high pressure. That's where you go. It's going out on high limit. Then you have the internal pressure release. This valve opens when the discharge pressure greatly exceeds the suction pressure. The open valve reduces the pressure difference and routes gas toward the motor protection system to stop compression operation. That's what protects your compressor from getting too hot to it, that it just melts everything on the inside. So parts of the compressor, you have the top plate and cap and muffler plate. Right underneath that, you have a scroll set, now which is a floating seal, and it kind of looks like almost like a main bearing or chase bearing, and it has little, I want to say they look like magnets, but they're little metal circles around the outside, like if you was to take diamonds around a jewel or a gem in a ring. This is what it looks like. But it's a floating seal. It provides a protective seal for the discharge of the screws and also places pressure on the screws to keep them in compliance. So you've heard people that say, well, it sounds like the screw separated. Well, that's almost impossible, so that's just wrong terminology. To understand a screw separation, these screws are made to where they have lift, okay? And there's maybe, let's say the screws are about 2 inches deep. So that lift is about 1.5 inches. When it reaches that 1.5 inches, that scroll set, that little thing, it looks like a little bearing, sits on top of the scroll, and that hits the muffler plate. And so in doing so, it keeps the scroll from separating. So the only way a scroll could separate is if you didn't have the floating seal and you didn't have the muffler plate, and that would allow the scrolls to completely come apart. But I've heard that terminology a ton. It sounds like the scroll's separated. It's impossible for that to happen. Now, in the LGs, they take it a step further. Excuse me. And on the scroll set, they actually have a spring that goes against the muffler plate and down to that scroll set to keep that scroll set from bouncing too much, to make sure the scrolls stay closer together than in a Copeland. A Copeland gives them a little bit more travel room. All right, the fixed scroll, it's attached to the compressor. That's next. So the fixed scroll is attached to the compressor body, and it does not move. On the Copeland, there is a yellow plastic suction funnel that basically, when the gas comes in on a Copeland, it goes in this little funnel, and that's supposed to shoot it up into the scroll. The LG does not have that. So the LG is cooled by the actual refrigerant itself. As the compressor fills up, then the force of that refrigerant coming up and the pressure coming in pushes it up into the screws. But the Copeland has a little plastic funnel tube that tries to direct it, I guess would be the best term. And that's called a suction funnel. It's secured to the fixed scroll, and it's of the color yellow, and it directs suction gas directly to the scroll set. Now, the Oldham Copeland, it's Oldham Copeland, which is a circle with a triangle shape on the outside of it to cause it to orbit. That converts the rotational motion of the crankshaft to the orbiting motion of the scroll. So the crankshaft, you got to understand, the crankshaft is turning in a circular motion just like a rotor or a wheel. All right. So if you could look at it kind of like a camshaft in a motor, how they have the oblong cams that rotate and they lift, every time they rotate, they lift up a piston or a piston rod. This thing is kind of, the shaft is round, and so this Oddman bearing or Oldham bearing sets on that round shaft, and it moves in a orbiting fashion. Okay, so it allows the fixed scroll that is hooked to the Oldham bearing to orbit on a round shaft. So you have to picture that. That's how the scrolls start to move in a orbiting fashion, but the actual motor itself is spiral. Then there's an unloader bushing. I've heard a lot of people say that the unloader has come loose in a compressor. Well, that's unless you put water in the system is the only way that unloader bearing or bushing, because what it does, it goes on the crankshaft itself, on the actual motor shaft, and it couples the crankshaft to the orbiting scroll. It works in conjunction with the Oldham coupling to convert motion. So you're basically going to have the shaft of the motor, of the crankshaft to the motor, and then you have this unloader bushing on it, which gives it more of an oval shape, turns your round shaft to an oval shape. That oval shape fits on the Oldham bearing and creates that orbital thing. Then you have the orbiting scroll. Again, let me go backwards on that, because you've got the shaft, the unloader bushing, okay, the Oddman bearing, and then you have the orbiting scroll that sets on the Oddman bearing, and that creates the other one. Then you have the fix that's actually screwed in place. It don't move. So the orbiting scroll rides on top of the Oddman bearing and the unloader bushing. Okay, then you have your main bearing housing, which supports the upper end of the crankshaft, the rotary assembly. So you have the shaft that comes up, and like I told you, the bottom sits in a section seated where the oil is, and then the top of that sits in this main bearing housing to keep it turning and keep it vertical. You have the bolts, and again, in Copeland has designed a triangle spring-loaded washer that connects and forces everything to lock against the shell. So when you look at how a compressor grounds, it can ground easy in a Copeland, because if your windings get hot and they touch any part of that metal shaft is then bolted and touching the outside shaft. So, when you're checking a compressor to see if it's grounded, you go to the copper that is actually welded to the compressor, and you test each leg, your run common and your start plug on your windings, to see if they're touching any of the housing or the copper. Well, on the Copeland, that triangle washer doesn't always mean that winding is come loose and melted and is touching the outside casing. It could be touching part of the motor, and that motor is all bolted together, and these triangle washers are touching the casing, and it kind of can work that way. Where an LG doesn't have those, it just has a regular bolt, like in an engine block boat, and they just got them torqued down. There's no washers or anything spring-loaded to touch against the side of the scroll. So on a LG, if it goes to ground, the windings would actually have to basically come apart enough to touch the outside casing. So in an LG, if that happened, it had to really get hot for that to happen. You have your sleeve guides, which are the little bearings that go under between the bolts that go into the main bearing. And then you have your crankshaft rotor. And if you've ever seen this thing, it's kind of kind of a cool thing. It's got a crankshaft and it's got the motor. So you got a crankshaft, which is the metal shaft that couples the motor to the scroll mechanism, and then you have a counterweight, which prevents excessive vibration of the compressor during operation. Just like you'd put a weight on a wheel. There's a counterweight on top of that motor that keeps it from getting too out of balance. Then you have the rotor, which is the rotating part of the motor assembly that drives the rotation of the crankshaft, and that's where the windings set, is against that rotor part. All right. Then you have the counterweight cover, which shields the counterweight from the oil in the lower bearing, prevents the lower counterweight from agitating the oil. And then you have, of course, the shell, which goes into the housing. So this sets down into the shell, into the counterweight, and underneath that counterweight cover, that's where the oil to the compressor goes. So it tries to keep the refrigerant from mixing with the oil. And so that tries to keep that oil stays around the bottom of that shaft and keeps that shaft where it will turn. So when you see one that doesn't sound like it has oil in it, you'll hear a metal-to-metal grinding where that shaft is actually grinding in the middle. Like if you didn't put any oil in the compressor at all and it has this counterweight cover on it, then that's quickly going to overheat and seize and not even turn. So when you see a compressor that has that it's overheated and it's not pumping, then you can have a fixed scroll. One of the scrolls have cracked from moisture where they didn't pull a vacuum, or sometimes you can get copper plating where you didn't deburr your copper and that got into it and it was introduced to it, and that'll cause some copper plating, and so will the moisture. So I've seen some of these different things happen like that. So if a compressor shipped from the factory with no oil in it, and you put it in a system, well, the first thing it's going to do, it's going to start sounding like it's metal to metal, and then it'll seize up eventually, and it stops pumping. And then that can cause excessive heat to the whole entire compressor. So when you understand how compressors put together, your terminology will get better when you start diagnosing a compressor. And then you can, when you understand how it operates, you can listen for noise and say, okay, this sounds like the scrolls are hitting each other. Why are they out of balance? So they could be an oddman bearing that broke and would cause them to clang against each other. So you could have that. You could very well have a broke oddman coupler, and it's making the scrolls clap. Basically is what would happen in that case. So understanding the different components. And then on your lower cover, you got a base plate. It's at the bottom part of the shell that provides a reservoir for the oil and the structure to mount the compressor. And you have a lower bearing that supports the lower end of the crankshaft rotor assembly. And of course, underneath that, you have your grommets. But to understand the way the compressors are designed, they're designed to run in a orbiting fashion instead of a round fashion. And then we'll look at some of the different things. But one thing I want to talk to you real quickly about, and we're going to go to, this will probably end this segment because I don't want to bore you out too much, but to understand the working components of it. But understand compressors don't die, they're murdered. And when you understand what that means, it means compressors are built, they're milled to spec, they're built to last for a long, long time. But there's certain things that has to be done on every install, every compressor to make sure it is done properly. So you're going to have to not use a saw, not use a hacksaw, don't use a hacksaw or any kind of saw blade when you're cutting your copper tubing. Always use a tubing cutter and then deburr that. Don't use sandpaper. Don't use a hacksaw. Don't use a sawzall. Don't use anything that's going to cause copper dust or copper burrs or copper debris. You want to go with a tubing cutter and a deburring tool. All right. Then when you put your copper together, and then you got to learn the sweating in with nitrogen. So make sure you're flowing nitrogen through the system, and we'll talk about how to purge with nitrogen just a little bit later, probably after this podcast. We'll go into some of that. But with this one, you got to understand. So we got to cut with a tubing cutter, deburr our copper. We got to braze with nitrogen. All right, then you have to do a pressure test. ICP, recommends a pressure test at a minimum of 400 psi. I hear a lot of people say they do it at 200, and I'm like, how can you pressure test your joint at 200 when the unit itself is going to run higher than upwards of sometimes 500 psi in heat pump mode or in heat mode? You're going to run into some of the 520 pressure, so you're safe to pressure test all the way up to 600 if you want to do so to really ensure your joints are good. So once you pressure test it, you need to hold that pressure for about 20 minutes. Then you need to pull your vacuum, and they want the vacuum to be down below 500 microns, and hold that vacuum. All right, and then once you've done all that, then you're able to open up the valves and let the refrigerant come out and your system test run. But if you're not pressure testing at a minimum of 400 psi for 30 minutes, you're doing your own self-harm in doing so, but you have to pull a vacuum. If you don't pull a vacuum, let's say you introduce moisture into a system, guess what's going to happen to the scrolls? Guess what's going to happen to the crankshaft? Because you got to understand the electrical current going through the windings create like a magnet type field that happens, and this thing's going to overheat and overheat. If you don't have everything done right, you're going to overheat your compressor. You can crack your scrolls, you can crack the Oddman bearing, and you can do a lot of damage to those things if you don't do it right. Now, everybody that's a service tech or an installer knows you don't leave an open line set. You don't do it, in the rain. In some cases, you have to, because of the way the service tech business is, you have to install one in rainy conditions. So I suggest you put like a canopy over the system and you pull the vacuum for at least, an hour and a half, something like that, and at least get it down to 500 microns. If you're down to 500 microns, you've pretty well got a pretty tight system. So you should be good. Also, you want to change your vacuum pump oil before you do all this. And then we're going to go into our next section of part 2 is what are some of the common causes of a compressor failure. And it's so interesting to me that before I took all these classes, when I was a service tech, we always thought, well, the compressors come apart, the screws come apart, it's not pumping, it's not doing this. Or you get to where a compressor's grounded, you get compressor windings are open, and then you have a compressor that won't pump. So we're going to go over in part 2 of why those happen, what causes that, how to recognize that, and then how to fix that as well. So we hope you stay with us in the next podcast to come. We'll try to keep these kind of short and simple, and hopefully you'll enjoy it. And we do appreciate you tuning in. We'll see you next time.